So our next presentation, the title is Seismic Retrofit of Concrete Structures Using Externally Bonded FRP. And our speaker is Dr. Tarek Alkhrdaji. I would like to introduce him. Dr. Alkhrdaji has been involved in more than 600 projects involving structural repair and strengthening, many of which received awards from ACI, PTI, ICRI. Tarek is an active member of several professional committees, including ACI Committee 440, 562, and 216. Dr. Alkhrdaji has authored and co-authored more than 40 papers and articles on repair and strengthening of structures, and he is the current chair of ACI Repair Code and Subcommittee on Fire 562F. So let's welcome Dr. Alkhrdaji and let's hear to his presentation.
Okay, appreciate it, the intro, and I think Ken did a great job with the summary of the ACI 440, the new code. I think that was a milestone really for this committee. It's been working for more than 20 some years on developing the guidelines for FRP. And in the second part, what I'm going to present on is the applications of FRP for seismic upgrade of existing buildings and structures, concrete structures mainly. Another disclaimer similar to Kent, that a lot of the content in the slides are representing my opinion based on experience with analysis, design of structures, and to the application of FRP. We've been involved in many and extensive testing over the years and have developed lots of information and data points that help us really identify some of the design limits that I'm going to talk about for these applications. So seismic is really a very complex topic because it includes lots of pieces from the analysis, the approach for the analysis, determining the demands, the importance of the structure and what kind of performance we're looking for. And then after that, the design of the FRP or any other structural system using maybe not just FRP, concrete enlargement, steel components, steel plates, jacketing, etc. for the strengthening. And because of the time and because of the focus on FRP, I'll try to get directly to the main items related to the performance for seismic that we focus on. And these include performance of columns, performance of shear walls, and strengthening of diaphragms. So with that, let me start with columns. So for seismic application, there are many deficiencies that can happen in columns, whether some of them observed during earthquake events, and some of them also based on experience. And these includes some of them that are shown on the slide is the shear strengthening of columns under lateral load, the plastic hinge and plastic hinge performance and ductility and confinement, bar buckling due to lack of, for example, lateral reinforcements that can provide confinement to the section and bracing for the bars, and also lap splice failure. Older structures, they have a shorter lap splices used in compression, and that causes failure. The good thing is that FRP is really viable for strengthening all these failure modes, and I'll go over those in the next few slides. Some of these have been established, and you can find lots of design guides that address some of these failures, like concrete column, for example, shear and confinement. Others related to bracing, lap splice are still evolving. There are some guidelines out there. There's a lot of testing going on, but not everything we're talking about here has been codified. But like Kent mentioned, some of these will be in the future versions of the codes. Plastic hinge is specifically very critical because if you lose a plastic hinge and you get failure of the entire structure. So proper confinement, proper ductility, ability to achieve lateral drift to dissipate energy is critical. And this can be achieved not only with FRP, can also be achieved with steel plate jacketing or maybe even concrete jacketing. However, using FRP is relatively easy because you're dealing with lightweight material, easy to apply, very durable, and would not really affect a lot of the geometry or the appearance of the structural components. They're also very versatile because of the flexibility of the fabric FRP system, the hand-saturated on-site and installed FRP allows for addressing all different geometries, round, rectangular, or even odd geometries like you see on the photo to the right. So it's a very effective solution. So let's start with the confinement. How does it work? And then we'll dig into the details. For columns, when you apply axial load to a column, although we cannot see it by eye, it's actually going through some type of shortening. And that shortening results in lateral expansion, right? We always talk about Poisson's ratio and how things that compress get wider. That's what happens in concrete. That widening and expansion, lateral expansion, cause cracks in the concrete, mainly in the vertical direction. And under multiple cycles of loading, unloadings, concrete start peeling and start failing. And you end up with a reduced section and less capacity, axial capacity, lateral capacity of these columns. When we jacket these columns, or we jacket that failure zone, let's say plastic hinge, we're basically holding the concrete together and preventing it from falling apart. That can be achieved with FRP, can be achieved with a steel jacket. So the concept of FRP for confinement is not new. We've been using steel jacketing for many, many years. We know how does it work. We know the increasing capacity and ductility achieved with steel jacket. We're transferring that to the FRP. The benefit of FRP or external jacket in general is that when you confine the section, you maintain the entire cross section, so you don't lose part of the cross section. And by preventing failure of the concrete, you're increasing its axial capacity and ductilities. And let me show you an example how that can happen in the lab. Now, what you see in here is a sample for column, not column, but more like a concrete cylinder. It's basically a simple test done in the lab just to show the effect of confinement on concrete. But I want you to keep in mind that a real column with a large size and a smaller amount of FRP going to give you different behavior. The ratio of FRP here to the cylinder is relatively high, confinement ratio. But you see confinement were done with 1 layer, 2 layers, and 4 layers of FRP. And the lower chart or the diagram to the bottom, the blue one, that's actually the cylinder without any FRP. It's filled around 110,000 pounds, which for a 6-inch cylinder, approximately 4,000 plus minus PSI. And you can see the impact of adding 1, 2, or 4 layers. We're increasing significantly the strength. We're increasing significantly the ductility. I think Kent mentioned earlier, and I think it's also important to mention here, is that what we focus on in seismic upgrade is not really the increase in capacity. And also keep in mind that we have a good limit for how much we can increase in capacity for gravity loading. But what we focus on ductility is you can see the brittle concrete that failed at small displacement. Now we have a lot of ductility. That is very important for able to dissipate energy. If I move to a rectangular section, in this case we have short square columns, the behavior is different. You can see the confinement on these columns is less effective because of the cross section. The cross section is not round, so you're really holding the corners together. And if you imagine the flat surface as it try to expand, FRP sitting on that surface, we're not really to try to confine it as much. So the confined cross section, the effectiveness of the FRP is a little bit less. We still can see increasing capacity, 30, 40, 50%, 100% sometimes, depending on the cross aspect ratio, but it's of course less than that for circular section. In all cases, we see significant increase in ductility. When we want to take that increase in capacity in design, it's really relatively simple. When we can determine from the amount of FRP, the confining pressure, F sub L, lateral pressure that we confine the concrete with, and that can tell me or can provide by calculation what's the increase in the concrete compressive strength, F prime C. So F prime C, the concrete compressive strength, when I confine it, become F prime CC, confined concrete strength. And I just simply plug in that new concrete strength into the standard design equations, apply all the reduction factor, and calculate the increase in axial capacity. But again, we are not looking only into that axial capacity, we're looking into ductility. So concrete strength, function of the amount of FRP, and depend on how many layers, like for example, in this top equation, number of layers, thickness of layers, I can figure out what's the confinement. From the confinement, I can calculate what is the new or higher compressive strength, and I can use that in calculation. But we also can calculate, based on information we have from testing and a developed equation, what is the increase in the ultimate concrete strain. So when we design for a typical concrete strain of 0.003, some codes or standards use 0.0035, we know that with confinement, I can increase the ultimate strain of concrete and achieve higher strain, almost 0.005, 0.006. It depends, of course, on the concrete strength, the amount of the FRP, right? We also have an ACI 440, the design guide, and also in the code now, equation that tell me not only how I can calculate the ultimate strain, but also the full stress strain diagram of the confined section by determining the stiffness before and after failure of or reaching the ultimate capacity, theoretical ultimate capacity of unconfined concrete. So this chart, this relationship is very important because will help me determine the capacity of the confined column, and we'll go through that in the next slide, or a few slides. So if I imagine a column, okay, I'm trying now to increase not the strength, but ductility, because that's important for seismic. And I think one thing I need to mention here is ductility is important for columns, and not only in moment-resistant frame, but also in frames with shear walls. Because even when you have shear walls, you're going to have lateral drift. And the existing columns need to go with the existing structure, be able to support the axial load without failing during the movement of the structure. So sometimes we have to still strengthen the columns and allow for lateral movement, even though we do not have a moment resisting frame. It's basically a lateral resisting system consisting of shear walls. So if I look at that column is going to go through the formation, right? And there's lateral drift. It's approximately 25 to 2.5 to 4% of the height, depend on what you're trying to achieve, and this is just a general range. The actual number may depend on analysis. If I look at really half the column height, right? That half column height, it has a zero bending moment, so it's behaving more like a cantilever, if you wish, right? And it will have, as a result of that moment, and we'll have a rotation on that cross section, and we'll have an angle at the base that is giving me that rotation. So if I can determine the rotation at the base, and if I can determine the plastic hinge, which is going to help me determine that rotation, I can determine what is the lateral drift or lateral displacement for that column. Why that's important? Because I can use this approach analytically to calculate with the FRP confinement how much I can improve the concrete compressive strain, how much more rotation I can achieve, and calculate the new drift with FRP that I can achieve without failure of the concrete. If we go through that concept, if you think about it, when you go through lateral movement, there is initial elastic portion, and there is a plastic portion. And the plastic portion that is resulting from confinement with FRP is what I'm trying to calculate. And that can be done easily if I can calculate the curvature, what we call the curvature of the cross section. And that is the cross section that falls within the plastic hinge, in this case at the bottom, right, of this column. And that curvature can be used to calculate the rotation. The rotation times the length give me the lateral drift. That is the basic approach that is not applicable to FRP, but general mechanics of material, structural behavior issues that can be understood by many. The curvature, when I look at now, I'm looking at that cross section at the base of the column. That curvature, that section, when it goes through rotation, it has ultimate strain and it has a depth of neutral axis. And that curvature, right, I can calculate, which is equal to, basically it's a small angle, so it's equal to the tangent, equal to the strain divided by the depth, right? That will help me calculate that. So if I know what is that strain, I can calculate that curvature, and from that, the rotation. And if I look at the impact without FRP, which is the section I'm looking at, once I add the FRP, I'm going to change the behavior. So if and what you see in here on the slide, actually the results from an actual test pulled from literature. A column that doesn't have confinement will go through some cycles, concrete start cracking, start falling, and you get failure of the section. So you can calculate, and you can see not a lot of ductility in this section. Once I add the FRP, I'm going to confine it. I'm going to allow it to take more rotation capacity. As a result of that, this ultimate strain going to increase. I'll be able to rotate the section much more without failure. And if I look at the experimental results, you can see that effect of the FRP. Now I'm taking more capacity. You can see I'm not increasing a lot the axial capacity because I'm not increasing the load. I'm just keep pushing the column back and forth until lateral load cycles. And you can see there's higher ductility been achieved. Now that same cross section, if I'm looking at the moment curvature, things we've done in school when we're doing, studying concrete and doing analysis, I can determine what is that ultimate condition with the ultimate strain, what is that curvature and that of yielding, and I can calculate from that what is the rotation, right? By taking that change in the angle times the height times the plastic hinge length, I get the total rotation that I could achieve at the plastic hinge. So this equation, what you see here, is almost like simple, like integration, calculating the total. I have the section keep rotating, and it's not one section, multiple sections within the plastic hinge. I'm adding up all how much they're going to rotate each section and calculate the total angle, and that will be utilized again by multiplying that by the height to figure out the total delta, which is the equation to the bottom of the slides to the left. Plastic hinge length, how do I determine that? There are actually many equations available out there, all give you plus minus similar results. If you look also on different standard, the US versus Canadian versus New Zealand, they all have different equations similar to concrete. I mean, most codes and standard give you results within plus minus, but sometimes the equation is a little bit different. One thing to keep in mind is that when we do seismic, we push things to the limits, right? So we are not using only the yield strength, we're using the expected yield strength. Sometimes based on quick, lateral loads, impact, there's some impact into that, you can achieve higher yielding. And some of you have been involved in testing. I'm sure you've seen that most of the time the actual yield is much higher than theoretical yield, whether it's, let's say, in 60 KSI for 20 or 400 MPa, depending on which unit you use, the actual is higher. Just want to visually give you the performance and the effect of the FRP. So here you see a setup representing a column subjected to axial loads, some minor axial loads, it's probably 10–15% of the capacity, and then lateral load cycles. And you can see the improvement in the behavior where you see in the red curves, this is the hysteresis for the column without FRP. Once I add the FRP to it, I can increase significantly, you can see increase in ductility, and more importantly, the area within the curve. This represents the area that can be dissipated, the energy that can be dissipated. You can see the area under the curves in blue or black, which has been done with black with carbon fiber and blue with glass fiber. You can see both materials can achieve significantly the energy dissipation and the lateral movement, and that is the thing that we're trying to target. So using this approach based on target deformation, I can go through detailed analysis, calculate what is the plastic, how much FRP I need to provide that confinement using the equation we went over, and then start applying the FRP. And typically the way we've done in the actual applications is we have what we call a primary jacket. That's where the plastic hinge confinement. The height of that jacket is typically equal at least to the longer dimension of the element or diameter of the column. There are some standards and codes. I think the Canadian, for example, use minimum 1.2 or minimum 2 feet, 600 millimeter equivalent. So it's different from standard, but all focus on confining the plastic hinge length that you determine from calculation. But imagine as we start move back and forth and we preventing it from failing, that plastic hinge may shift a little bit up. And to address that and prevent failure of the concrete as it starts moving potentially, we have what we call secondary jackets. It's a jacket that's the height of the jacket is commonly is half the height of the plastic hinge jacket, and the number of layers are applied is half the number of layers of the FRP used for the plastic hinge jacket. So the A times E axial area times the stiffness is basically, I'm trying to achieve total stiffness that is half, which is basically half the number of layers, give me that. Other things to consider is that we're trying to confine, so we round the corners to 1/2 inch radius. Some standard, I think the Canadian, they use 20 millimeters. I'm not sure if what's the other standards would call for. But the idea is I'm preventing the stress concentration of the corner that can cause rupture of the FRP. And other thing related to detailing is on the bottom of the column, I would leave typically 25 millimeter or 1 inch gap. The objective of that is to make sure that as the section rotating, I'm not applying compressive stress to the FRP that may cause also premature failure. I myself was involved in a test in which we did actually extend the FRP all the way to the base of the column, and we did see premature failure as it started to buckle at the bottom due to that compression, and that caused premature failure of the jacket. So the 1 inch gap is an important part of detailing. Now that we address column axial, I have to keep in mind that, I increase the ductility. Now it can move, but that same column is under lateral load is going to have higher shear. So I need to prevent shear because shear is a brittle failure mode. It's sudden, doesn't give me any ductility. And if I do the same test or similar test that we've done earlier for column under lateral movement for plastic hinge, on a column that's deficient in shear, I can see here in the red cycles that it's brittle. So I'll go a few cycles and shear failure suddenly would fail. When I add FRP, I increase the shear capacity. What you see in here is basically there is more ductility, not because shear is become more ductile, but rather I'm avoiding the brittle mode and forcing failure based on steel yielding, and steel yielding gives me ductility. So addressing shear and pushing the failure mode into a more ductile failure mode based on steel yielding, of course, give me that increase in capacity. For the sake of time, I'm not going to spend too much time on the equations, but the shear design for column is not that much different than the shear design Kent earlier showed for the for beams, for example, where we have a strain limit, and of course strain times the modulus give me stress. So if you think about it, 0.004 strain, and if I multiply by, let's say, high stiffness material 14,000 KSI, give me a stress approximately 56 KSI. So it's not really that much than steel, but it's limited to this low number, which is almost 25% of the ultimate capacity, just because I want to make sure that I don't allow for too much deformation, too much cracking, too much movement. That is the main concept. And similar to steel reinforced, I want to make sure in shear I'm not going to get brittle failure mode by crushing, right? Because there is a truss action going on in shear where the steel taking or FRP taking tension and the concrete still taking compression diagonal strut. So I want to make sure this failure mode is not going to happen, and that's why there's an upper limit on shear. Now, if I need capacity more than this upper limit, FRP is not going to help me because it's controlled by concrete. I need to think about something else like concrete enlargement and then confinement, or concrete enlargement with a lot of ties that add more capacity, concrete capacity, as well as confinement reinforcement. Lap splice is another application where I mentioned historically short column splices in compression have been used, and when you put that same structure into a lateral load, you can start slipping of this lap splice, because the lap splice need concrete around it, right, to be able to transfer the load between the two bars. And if you lose that, then lose that concrete, that interaction with the concrete around it, then the bar is not doing anything. As a concept, I have a bar, it has adequate lap splice, I apply tension to it, it will achieve the full elastic and then give me plastic behavior beyond that. And if I do not have adequate lap splice, then at some point, maybe even before I reach yielding, then the lap splice would fail and I would not be able to achieve the ductility that's needed with FRP. That ductility is needed in general. So again, if I look at the behavior, short lap splice, I apply load to it. And again, this is similar to the previous case from experimentally what would look like. I get sudden failure because I do not develop the yield capacity. If I add the FRP, then I achieve yielding, and that gives me the full capacity I'm looking for and the ductility. So short lap splice, brittle failure, similar to shear, we don't want that. Doesn't allow us to achieve capacity. Here are some tests for lap splice confinement that we've done over the years. This is an example of a 12 by 12 inch column with 4 corner bars, number 8 bars, 25 millimeter diameter. You can see in blue is the control column where you suddenly get a failure of the lap splice, so we don't achieve lots of ductility. You confine the lap splice with FRP, you prevent the concrete from falling apart. You hold it in place and continue to transfer load, and we'll be able to achieve yielding. You can see the ductility that's been achieved. One thing interesting in here is you can see the green line is 4 layers of FRP, red line is 2 layers of FRP. So basically there's a limit of FRP beyond which you don't achieve more, right? Because you already was enough, you achieved with that FRP, the yielding of the bar. Beyond that, you're not getting anything else. So that's helped us also understand the behavior so we can optimize the design for clients in general. And this is another column, 16 by 16 with 8 bars. So 4 corner bars and 4 bars in between. Again, you can see black is the failure of the lap splice, and you put FRP and you can achieve much better behavior because you're achieving the yielding, higher energy dissipation, and achieve the ductility of the column. When it comes to FRP, when I combine all these together, typically what FRP would look like is you see more layers in the plastic hinge region, in this case top and bottom of the column. So you see here, for example, 4 layers of FRP. You can see a transition zone, which is the jacket, the secondary jacket. This is, for example, 36 inches and half of it is 18, 4 layers, 2 layers. And in between is going to be controlled by shear because I have enough FRP to address shear at the end, a lot of FRP. In between, if there's a shear deficiency, that need to be also addressed. So you see whatever is needed for shear in the center of the column. And of course, it's different. The layout from case to case depend on the condition. This is one example. You can see in here couple of examples for FRP confinement. The photo to the right is actually a flared column. This is US 50 in California. And the plastic hinge occurred at the bottom of the flare, which is the location of, unfortunately, the lap splice in this column. So there's a lot of FRP was applied right at the bottom of the flare, the top flare, that is used for plastic hinge confinement and lap splice confinement. The top portion was wide enough, has included adequate capacity, but the Caltrans specified additional FRP on the top just for integrity and minimize cracking. So otherwise, you really do not need the top, maybe 2 feet or 3 feet may not require FRP in this case. So that is for the column. If now we come to the other critical element, which are shear walls, right? The main lateral load resisting element that we can see in many of the high rise. And if you think about a shear wall, it's almost like a vertical beam, right? That is taking shear on it. But also these walls are subjected to flexure. Potential failure mode is a shear failure mode, a 45-degree crack. Again, you try to push it and you get a 45-degree crack. The shear demand is different from level to level, right? When we do seismic analysis, we accumulate the mass, and as we go down, the shear increase, the demand on these walls will increase as we go down. So we may find upper levels that are adequate, lower levels that need some strengthening. Other potential failure mode is a sliding that can happen typically at the wall to slab connection, where there's too much force on it. We've seen that actually in masonry more than concrete, but I've seen some cases from historical earthquakes. We can see a horizontal crack that's really causing the wall to slide and you get failure. And the other thing is that the shear wall, it's like a vertical, very tall cantilever. It's also will go back, swing back and forth. In doing that, it will go in bending. So there's a shear component and there's a bending component on these shear walls. That flexural component may require actually confinement, because sometimes it's not tension failure or it's tension failure, and I can strengthen for tension, I end up with compression failure, right? So either you increase the width of the wall to minimize the stress on it, or you need to find a way to confine it to increase the capacity of the concrete, right? When we design new structures, we have confinement at the end of the steel walls, right? Why we confine that? Because that concrete is in compression. By confining the concrete, I can increase its capacity, compressive capacity, and ductility, delay failure. That's what we can also achieve with FRP. Here's an example of a failure of a shear wall with a 45-degree crack. Again, lower level, it's a higher shear demand in here. FRP, typically how it's used, we are trying to mimic internal shear reinforcement in a wall, which we put it horizontally. Why? Because the shear now is horizontal direction, right? Not like a beam in the vertical direction. And the layout of the FRP may be full coverage, maybe strips, depending on the efficiency, could be on one side or two sides of the wall, right? So all these applications are viable. In terms of the design, there's a design criteria currently in ACI, which has a limit on the strain that I can calculate, and from that determine what is the design stress. And the design equation is, again, similar to beam shear. So it's not that much different. If you design with the steel, you would know that the design for shear is area of steel times the yield stress, Fy, times the depth divided by spacing to figure out how many stirrups I'm going to interrupt to the 45-degree crack. So the concept is the same. There's not that much difference, except that we're using area of FRP, stress of the FRP, and then the depth of that wall. Currently, I mean, depend on whether FRP on one side or two sides. It's assumed that for one side is less effective, so we use 0.75 rather than 1 if it's on one side, while on two sides it's considered more effective. I think this is a gray area, honestly, depending on the test results we've seen. And there are some standards that use 1 and 2, and there are others that use 0.75 and 2. Also, the effective length of the wall for analysis depend on the standard. Sometimes I've seen assumption made from face to face of the piers at the end. Some codes, I think like the Canadian S806, for example, I think they use 0.8 times the length of the wall. So that, again, depends on the standard, but in general, it's similar to what we use for steel. And similar to typical shear, I have an upper limit, because as I go and increase the shear capacity, at some point, due to truss action, there's a compression component that may fail concrete in compression. If I reach that limit, I'm not going to be able to use any more FRP. And I need to think about increasing the concrete mass, the capacity, and that may require enlargement by shotcrete, form and pump, by simply roughening the surface, adding dowels, rebar, and adding 3 or 4 inches to the thickness of the wall. And similar to stirrups in beams or even or lateral reinforcement in shear walls, I need to control the spacing. If I allow these strips to be too far apart, then they may not be very effective, or there are some cracks I may not be able to capture them. So there's a requirement and to control the spacing to ensure that every crack is adequately captured by the horizontal FRP reinforcement. And here are 2 examples of the FRP on walls. You can see strips, you can see more coverage, sometimes 1 layer, sometimes 2 layers, 1 side, 2 sides. Again, it's a function of deficiency, and we can calculate that and determine the amount of FRP is needed. I think one thing I should mention, just to make sure there's no confusion, since there was a question to Kent earlier, is when we deal with seismic, there is no typically upper limit for the FRP. So there is no requirement that we can, the structure can take 75% without the FRP, because seismic is an extreme event. It's one in a lifetime that may or may not happen to the structure. And when that happens, we're trying to get as much capacity as possible to prevent failure of the structure, improve the life safety and safety of the structure in general. So the code allows us to fully utilize the capacity of the FRP. because again, it's an extreme event, less likely something happened. And the concern why we have the limits in gravity load, not in seismic, in gravity, the idea is, what if someone damaged the FRP? I think Kent answered that question. Is the structure maybe sitting there for 20, 30 years, someone doing a renovation, they cut the FRP, we want to make sure the structure will have adequate capacity until we repair the FRP. Seismic, you have typically more loads, more time. If somebody damages it, you can capture that. Less likely we'll have a seismic event in between, and you're strengthening the entire structure in general. Same thing applies to masonry. I know we're talking about concrete, but there's masonry also can be strengthened the same way. There are guidelines how you increase the capacity of shear walls that are made of masonry. What you see in this case, actually the FRP is a glass FRP, because a masonry wall has less shear demand, less shear capacity, you don't need carbon reinforcement. And glass, when you saturate it with the resin, especially if the resin has neat resin, doesn't have a color, as colorless, you can see almost through it. So this is FRP glass fiber already been applied. And what you see at the base in here, there was a concern with the transfer of the forces from the wall to the slab. So there was a strip of concrete removed, additional dowels were placed and cast back to transfer the force from the wall to the slab. Here are another photos for masonry. You can see to the right, horizontal reinforcement, and to the left, which I'm going to talk about next, is FRP horizontal reinforcement as well as vertical reinforcement. And these are made with the NSM bars, near surface mounted or surface embedded carbon bars, to give me that bending capacity, which we're going to address. One thing to mention is the flexibility of FRP. So in this case, I have a staircase, metal one, and we had to drill, actually long drill bits, and drill behind along the surface and use what we call concrete FRP anchors. It's basically bundles of FRP that would go into behind the wall, splay on the FRP on both sides, and transfer the wall. So there is some flexibility in using FRP with these anchors to transfer the forces if I have interfering elements in place. Now we talked about the shear. If I look to the right half of the slides, we talked about also bending. And I mentioned that you can add vertical FRP to provide that tension reinforcement for bending. And you can also confine the ends to increase a little bit the ductility and be able to achieve higher bending capacity if it controls the failure mode. And that layout of the FRP will be different. So the photos you see on the screen are shear wall strengthening, and you can see there's a higher level that has less amount of FRP and lower level that has more FRP. That's because there was a discrepancy in the original design. This was building still going under construction, and they captured an error in the construction, and the amount of deficiency was higher on the lower level and less on the higher level. And the lower level also had some flexural deficiency in the wall. So we can achieve that by bonding vertical FRP on both ends of the wall to allow for that rotation and the ability to achieve the bending capacity. And of course, the FRP need to be extended enough to develop the FRP and transfer that bending to the wall section above and below as needed, right? Sometimes you don't need to go above, maybe only below, and above just a little bit need to be extended for development. But there are other ways we can do it. So this is just a schematic, not an actual thing, just to show different things we can do. We can cut grooves and put vertical FRP bars and get that flexural, continuous flexural reinforcement, which require drilling through the slab to be able to get continuous bars. You can use a combination of bars and strips, like for example, using FRP strips between the slabs, drill and put NSM bars and create adequate lap splice between the two. So all these applications are viable. Here you can see this is inside elevator shaft. An elevator shaft, typically the walls are used for shear, and you can see grooves cut with in the vertical direction where they're installing surface-mounted carbon bars to achieve that bending capacity with that wall. Nice thing is working inside the shaft. There are no slabs inside the shaft, so you can run the bars continuously. Now the bars have length. like steel bars. So at some point you have to create a lap splice, which means at certain location at the end of the bar, you cut a little bit wider grooves and you put the bars next to each other, and there's a way to calculate what's that lap splice length for the FRP bars. Here you can see a masonry wall that's been strengthened with FRP for shear, horizontal strips, and also you can see vertical strips at the end for bending. So what's happening, if you look at the right photo, this is an existing wall where the owner wanted to cut a big opening in the wall. When you cut an opening, you reduce the shear capacity, right? You reduce the section. So the remaining portion were strengthened to take the full load and make up for the lost section from the opening, right? So we have now big piers, and both need to take shear and flexure. And of course, flexure need to be anchored all the way to the bottom. You can see here on the FRP, there are some anchors being installed, which is something we're learning that is under lateral load movement. It's better to anchor the FRP as a minimum at the end. And now we're finding that sometime intermediate, depending on how much FRP you're putting, intermediate anchors may be needed to make sure that everything is working together and there is not a lot of debonding that results from cracking under lateral load, significant cracking that may cause debonding of the FRP. So that is related to shear walls. So we talked about the columns that they need to move with the structure. We talked about the shear walls that they need to take that lateral load, and why it's important, because we're always upgrading and modifying existing structures, cutting openings into existing walls, evaluating structure that were built 30, 40, 50, 60, even 100 years ago and find they are laterally inadequate, and FRP is a good way to achieve capacity. Now, the load coming to the shear walls is coming from where? From the diaphragm, right? The slabs that within the structure, as they move, right? They move as a deep element, and they need to transfer the mass, that inertia from the mass times the acceleration from the seismic load to the wall. So the walls would not do anything unless they have some load, and load coming from the slabs, and the slab themselves, as they move, they have capacity that need to be achieved, right? And we'll go through that in a little bit more details. Diaphragms are a little bit more complex, right? Because in reality, we don't have a simple, basic slab rectangular, as I'm going to show in the next few slides, a simplified example. We have an odd shape for these diaphragm, and we have shear walls that are not uniformly distributed, and we have openings. So detailed analysis with like finite element-based software is important to be utilized so that you can determine exactly the demands, shear demands, the forces, the cord collectors, the drag forces going on within each floor that need to be strengthened with FRP. If I look here at a simplified, again, I try to use a simplified approach for this diaphragm. And when I'm looking at, imagine a floor. It's a very basic model. I have a floor. I have two shear walls at the end. And if I have the inertia for that movement, right, the mass times acceleration, that's basically the basic principle of the force generated from lateral movements. That is basically acting as most like a uniform load. So this is, if you imagine, more like a deep beam with a support, except that it's in a horizontal direction, right? And it starts moving back and forth, it will go through bending. That bending may create tension in one end and compression on the other, and as start moving in the other direction under seismic load, reverse that. So the tension will be required on both ends of that slab. That's what we call cord. Cord is a tension reinforcement for that flexure, right? I'm also going to have some shear forces on these diaphragm, and then there is some transfer of forces from all this mass to this one point of connection. I need to make sure I'm collecting all these forces and transfer it back to the shear wall, which are the basically collectors, right? So these are the main components, and let's go through them and think about them. Again, was trying to put this very quickly, so it's not the best schematics, but I hope that everyone will be able to understand. So if I imagine this slab, right, in horizontal direction, like a beam, it will be exposed to bending moment, like I mentioned, and shear, and that will create demand in both tension, right? As well as in shear demand and, as I mentioned, in transfer. So if I take them one by one, first in bending, and we said that if this deep slab or beam goes in bending back and forth, up and down in the plane of the screen or the slides, you'll see that you'll require some tension reinforcement at the top and the bottom because going in load reversal. So I can determine from seismic analysis what's that tension required. And because I don't have adequate internal steel, I can mimic it and achieve the same capacity with externally applied FRP. So this FRP will basically give me that capacity I'm looking for. And the photo to the right show you an example of that. Now, the amount that is needed depend on the deficiency. Sometimes you need to put one layer, two layers, 24-inch wide, 48-inch wide. If it's a very deep structure, sometimes we've seen 6-7 feet depth of FRP that's needed to be able to achieve that demand. You can also do it on the top and the bottom of the slab, but on the underside may not be feasible. You may have some transverse element, joist or beams, or other things that may interfere with the application of the FRP. So typically you look at applying FRP from one side. If needed, you go to two sides. Okay, so that is the main concept. In terms of design, we try to mimic this using the ACI approach, and it's also in AC 125, similar to flexure, because really it's a deep beam going into flexure. So we use the limitation for flexure that give me what is the strain of the FRP. I multiply by the stiffness, give me that stress, could be 40, 50, 60, 80 KSI. And once I multiply that by the area of the FRP, which is number of layers times the thickness times the width, right? I can determine what's the total force I'm applying. Reduction factor are different from standard to standard, code to code. For example, if I'm designing per ACE 7, I may need to apply a reduction factor. If I'm using ACE 41, I may not need to use reduction factor. I may need just use 1.0 for all these reduction factors. So again, depend on the analysis type, the codes, the standards that controlling the design. So now I have these slabs that is moving, right, in shear. And we said that we need to collect all that force at the end and transfer it to the column. So it's what we call, in a simple way, a collector that has, at the end, if you imagine that's the free end, right? And as I move toward the column, I have more and more the mass contributing that I'm trying to transfer to the column. So that demand increase as I get close to the, not column, in this case, shear wall. So I'm trying to collect that forces and transfer it. Again, when we do analysis, we determine what's the amount of the steel collector and we design it for new construction. But if I'm dealing with existing structure, I do not have that, then I need to calculate what's the required collector or tension reinforcement, how much I do have in place, what is that delta, the difference, and try to mimic that with FRP. But the difference here between this collector and cord is collector is almost under axial tension, right? The flexure is really in bending, so strain is maximum and then reduces. Collector is slightly different. There is some different theories about that as we start, figure out how to design for the FRP. But because of that, the design requirement for FRP for collectors is a little bit different, right? In terms of design strain. If I look at that floor slab that we talked about, then the FRP would be applied similar to mimic that steel required for that collector. The design requirement is a little bit more aggressive, so less strain. I'm utilizing less FRP because from tests, from experience, we know that FRP under axial tension typically give you less capacity than when you are applied in bending. It's similar to concrete in bending, have higher tension capacity than in pure tension, right? So one is close to 4 square root of prime C in axial tension, but when you put it in bending, you can go up to 7.5 square of prime C plus minus, again, depending on the standard, but this is just to give you a sense of that. Again, depend on the area, number of layers, thickness, I can determine that tension force, and I can apply the FRP to achieve that capacity. So now I address the bending, address the transfer of forces, the collector. But this slab we mentioned, it's a deep beam, so it has shear on it. And I can look at it similar to a beam. I have a deep element that has in it concrete and steel that can utilize to determine the capacity, shear capacity, and I need to determine how much deficiency I have, supplement that with FRP. In this case, it's really the movement in the plane of the slab, and the reinforcement is needed in the direction of the shear. Now, keep in mind, in reality, the structure not only moves in one direction, but in two directions. So I'm looking at it in one direction, but whatever we talk about today in terms of cords collector need to be sometimes in two directions if I have deficiency. So you may find FRP around the perimeter of the building for cords in two-direction bending, and then you find FRP in two direction on the slab itself for shear in two directions. Could be similar, could be different, depend on the geometry, the force demand in each direction. But again, now I'm trying to address shear. So I have, imagine like a deep beam, I have 45-degree cracks that's happening through the slab as it goes through movement, and I need to put reinforcement that's in direction of the shear, crossing that crack to be able to prevent failure in shear. So that is achievable with FRP, but again, similar to any other design criteria, I have to control spacing. I need to determine how much FRP I need. We don't want to put the FRP too wide apart, again, become less effective. So we need to capture a crack with as much FRP as possible. Design criteria, currently we use a criteria similar to shear, beam shear, which is a little bit conservative. If I look at the typical design, there are some way to calculate that, depend on the geometry, the concrete strength that you have in place. I can determine the design strain without any anchors. We're talking here about a strain of roughly 0.002, which give me maybe around 36 or so, 38 or 30 KSI in terms of tension. So I'm not utilizing FRP to the full capacity. I'm trying to reduce that because I want to prevent the concrete, the openings of the cracks. I want to make sure also I'm utilizing the stiffness of the FRP to make sure everything is working together. Design criteria is similar to the criteria we talked about before for beams. And the reduction factor depend on the codes or standard you're using. And of course, even these limits, the strain I'm talking about, I'm referring more like the US, the way we design in the US, but other standards may have a different way to design. So the strain could be plus minus. Not only that, if you look at the bridge design standard versus FRP for bridge application, like the I-02 standard for FRP versus ACI for buildings, you also can see variation in the design criteria and the strain upper limit for the design. So it's all based on experience and testing for each of these applications. Here you can see the FRP layout for the diaphragm. Again, strips at certain spacing to achieve certain capacity. It can be in one direction, can be in two directions, depend on the deficiency. So it would vary from project to project. So now other failure we have not talked about is the potential failure under lateral load, which causes a sliding of that wall. And typically I mentioned it happened at the connection between wall and slab elements, right? All this force shear coming down from the wall, or the shear transfer from the slab to the wall needs to transfer at that connection to the wall. And if you don't have adequate shear capacity, it will fail, and you're not going to get the transfer of the load to the wall. So you're not going to engage the wall, and then you're going to get failure within the structure. How do we achieve that? Is basically by, typically if I'm looking at new design, and this is just one example you see on the screen, but typically we put additional steel that connect the slab to the wall to be able to transfer that shear force. But if I'm dealing with existing structure, I do not have that internal steel, I can mimic it with FRP that can be used to transfer this load. And this is what it would look like. The FRP would basically be an FRP applied at the inside corner, right? Which is basically the transfer between the wall and the slab. The FRP typically in this case is a plus minus 45 degree fiber. It's not really zero degree and 90 degree, because as the wall go back and forth, right, I need FRP in 45 degree to engage in tension in both directions, right? So that is critical. Sometimes I can achieve this with FRP applied to one side of the slab, and sometimes if I don't have enough capacity on one side with FRP, I can put it on two sides, above and below. So now really I have twice amount of the FRP connecting the two elements, transferring the load from one to the other. The diagram that you can see in the middle of the page is a connection without the FRP and with the FRP. And you can see without the FRP, at some point you get shear failure just from the separation. The crack would generate along the interface through the concrete, and there'll be no load transfer. That is the black diagram in the middle, and you can see it's going under, it's lateral, testing, dynamic loading, tension, compression. And then with FRP, you can see a significant increase in load transfer and allowing some movement. So there's generated some, I don't want to call it ductility because it's not really that much ductility, but you can see it's improved in the behavior of the transfer of the loads. There's a lot of tests. Most FRP manufacturers have developed tests and criteria for this shear transfer. From my experience, you can achieve between 8 kip per foot of shear transfer to 20, depend on the layout of the FRP. And you can also, if you put anchors in the FRP, you can achieve that 20 kips capacity. If I put two sides, I may be able to increase that and double it in some cases. So these are the main applications for seismic upgrade. Again, we're trying to, because of limited time, I did not dig deeper into the technical aspect and specifics related to design. As I mentioned, I'm trying to present the big picture, but there are other applications besides these ones that we talked about right now. For example, we have coupling beams, right? We have shear walls and we have coupling beams in between that are subject to high shear, right? And also bending forces on them. And we have done tests, and others have done tests that shows that you can increase the shear capacity of coupling beams and increase their flexural capacity. Things to consider for elements like coupling beams is you need to fully confine the section, because that high movement, high shear, high bending will basically create a lot of cracking in the concrete. So full confinement is required. And if you think about it, when you have these coupling beams, which is the small beam above a door or an opening that connect two big shear walls, you have a slab most of the time on the top side, right? Let's say if you have elevator shaft, you may have a slab on one side. If it's intermediate shear wall, you may have a slab on both sides. So you need to be able to confine the beam. You have to go through the slab, which means you may have to drill holes through the slab and use these FRP bundles to go through the slab and extend them down, and then put the FRP and provide that confinement that is required. And if you look at new design for coupling beams, we have a lot of steel in them. We really try to provide confinement ductility. There's also the wall ends for flexure. I mentioned as the shear wall goes in bending, sometimes you have failure and compression of the concrete. We can wrap the end with FRP and put through anchors with FRP and create that confinement with post-installed FRP compared to and try to mimic internal steel reinforcement. So there are many similar applications like that that can be done to improve the performance of seismic capacity. Again, the major task, and that's in the front of the ACI committee, Kent mentioned that. I myself, like Kent, been a member with the ACI committee for many, many years, since 98 approximately, and then now part of the dismantled code committee. There's still a lot of work need to be done. We're still collecting, working this data. We've done a lot of tests, so we understand the behavior very well. We can calculate the contribution of the FRP, but it's time to really codify that. We have some of that already in design standards, but now need to expand on it to cover all the application I mentioned and discussed during my talk today. So that's all I have for now, for today. Last thing is you can see the application I mentioned for that FRP for shear transfer. And it is, again, looks transparent because it is a glass fiber. It's not very heavy application. The reason for that is this building has lateral load demand for shear transfer, not from seismic, which is much higher typically than wind, but rather in this case, we have wind. So this is a building in New York. The design on the East Coast is controlled many times, depending on the location, for high rise, of course, by wind, rather than seismic, which control the design on the West Coast. So lighter layout, that's why you see strips at larger spacing. Glass was able to achieve this load transfer. Other application, I did not include a photo, could be a complete coverage from end to end with carbon FRP, again, bidirectional plus minus 45 degree to transfer that load. And with that, I conclude my presentation, and we still have, I'm assuming, enough time for questions. And one thing I wanted to mention, again, lots of information I presented today, very compact, but trying to explain the application. I put my email on the slide. Feel free to copy it down if you have any questions related to this that we may not get a chance to address today, or if you need additional information or you want to discuss a certain application, feel free to reach out. I'll be more than glad to work with you or help you with whatever you're looking for.
Thank you, Tarek, for such a great presentation. I mean, you covered very important points for this seismic, as this is the major concern in many cases for this kind of application. So we do have a few questions. We'll go through them. So our first question is, for shear transfer at diaphragm, please confirm that bidirectional fabrics are utilized.
For the shear transfer, yes. I think I mentioned that a couple of times. You need bidirectional fiber, typically plus minus 45 degree, because the structure moves back and forth, and you'll be able to take tension in both directions with the fiber. So yes, bidirectional fabric is needed most of the time for these applications.
So our next question is, when you drill through the slab, do you shore it for temporary destruction of the shear capacity of the slab?
Not typically required. Well, first, it's a process. It's a destructive process. Strengthening is like repair. Sometimes you have to weaken the structure temporarily before you strengthen it, right? That's true with any repair approach where you chip concrete or move steel out of steel. So it's important to do GPR. That's step number one. You don't want to drill and cut the steel bars that you already have in the slab. So GPR, identify the bars, top and bottom, identify where you can drill, and then drill. But if you think about it, if let's say you're putting this, let's say drilling a 3/4 inch every 7 inches, 8 inches, you're taking a small amount of concrete, 15%, maybe 10%, is well within the load factors and fee factor compared service to ultimate. So we're temporarily weaken it, but not enough to cause failure of the structure. If the demand is such that a lot of FRP need to be taken out, then yes, shoring need to be considered. So that's part of the responsibility of the designer to assess this requirement, and shoring and structural stability is always a responsibility of the engineer, right? So.
Yeah, thank you. Our next question is epsilon sub FU the failure tensile strain of the GFRP? So yes, I think it, yeah.
Yeah, it is. Epsilon FU is basically, you stand for ultimate, F for fiber. So it's the ultimate strain of the fiber. It's not just GFRP for carbon fiber, for even NSM bars. It's the standard term referring to the ultimate strain of the product being used in analysis.
Mm-hmm. Okay, thank you. Our next question is, so most of your presentation did say the picture showed CFRP. So is all the design for particular FRP sheets, or it is applicable for all types?
So the fabric, it's applicable to all types. The only difference is the modules of the material is going to be different. The ultimate strain we talked about is going to be different in the equation, but it's similar. If we talk about a different system, let's say surface mounted FRP bars, it could be a little bit different. The ultimate strain is a little bit different because the FRP bar is embedded inside a groove. So the bond is better, and sometimes actually by standards, you can achieve higher strain of the surface embedded FRP bar than the sheet. if you remember, I showed this one example for wall with vertical bars. The reason why we did not put sheets, which are easier, at the end of the wall and selected to go with multiple bars, because actually the bars gave us higher tension capacity. So by using bars, it's more intrusive. It's maybe slightly more expensive, not that much an FRP sheet, but can give me higher capacity, and was able to achieve design with FRP using FRP bars. So the strain, the equation are similar, but the design values, strain and stiffness may be different from system to system.
There is a continuation of this question. It says, so does GFRP is better than CFRP or better than BFRP as in particularly to the seismic applications?
So it's all demanding capacity and how much capacity can achieve. The glass fiber is on the lower end because of its strength, right? Its strength and stiffness is relatively lower compared to carbon, which is the higher end. Give you an example, ultimate capacity of glass could be 70, 80 KSI. While if I look at carbon, could be 180 to 100 up to 300 or 400 KSI, depend on if it's pre-cured or saturated. So I have much higher capacity with carbon than with the glass. So for certain application like masonry, where it doesn't have lots of demand on it, glass may be more economical because it's also cheaper than carbon. But other applications, I need more capacity, so carbon makes more sense. And I can use glass all the time, but if I need more force, I'm going to put much more glass fiber. So I end up with more surface preparation, more installation. In North America, cost is controlled by labor more than the material, right? So this is the balance. So you can use any of these material. You have to go through the economics and the geometry, because ultimately, like with anything else, its cost really affect the which project or which system you will go with. But they're all viable. It's like if I'm going to use number 8 bar, large diameter, 1 inch diameter bar, I'm going to use a lot of number 3 or number 4 bars. I can use both, right? But which one makes more sense? This is more engineering judgment and financial assessment.
Yeah, we have 2 more questions. So do you have any suggestion to know which supplier is good enough depending on the type of fiber and resin used, and whether the resin have fillers, and how this would affect the design and durability?
Lots of questions. So at the end, I deal with certain system. I showed like the VRAP on a few slides. This is my experience, but there are other systems out there, all available. I think the other speakers are going to come representing other systems. Again, the way I look at it is people sometimes say, oh, this one better system than this one. It's all about properties demanding capacity. I can use a great 60 KSI bar, and I can use great 50 KSI bar or 80 KSI bar, right? So it's all going to end up with more material, less materials, more detailing, less detailing. All are viable, and everything can really be used. Certain applications make more sense to use higher stiffness materials. Some require less stiffness material. So I think in my mind, everything is viable as long as it's done correctly. I think the important thing is sticking to a standard, because you're comparing sometimes different manufacturers, and based on their own experience may have different approach to design, and that creates discrepancy more than the mechanical approach or the for the design and the design increase. But other than that, I would say everything is applicable. It's all based on design and the economics and the detailing required for each system.
And last question is, have you ever tested for the durability? For example, if the structure underwent seismic load and the repair has been done, and was the structure again did it sustain the loads later on?
So, well, there's, I think, durability, not in terms of material degradation, but in terms of performance before and after the seismic event. There are some events that happen, South America, Turkey, etc., where they actually have some FRP, and we've seen the behavior that's been really working. These structures that have FRP did not fail, performed adequately. There are also all the experimental tests and full-scale tests been done, are done under lateral loads on structures. Some researchers in Italy, I have some colleagues in Italy that's done 2 and 3 story building, like a half scale, and did the full testing on the structure, and you can see the improvement. The reality though is this, is sometime when we use FRP, we're not expecting to open the structure immediately to use, right? You can if you design for that design criteria, but it could be much more demanding. Sometimes we're preventing collapse, and we're just trying to keep it functionable for a while. So you still have, like with anything else, to come back and do repair, which means under the FRP, you may have lots of cracks. So you may need to figure out how to do the repairs after the events. So FRP from experience would work. That doesn't mean you're not going to end up with damage after the event that need to be addressed, similar to any reinforced concrete structure.
Great, thank you so much. So Tarek, thank you so much. Once again, we do not have any other questions, but if you have any questions, please reach out to Tarek. He already shared his email address. So thank you so much once again.